Hi everybody, welcome to the presentation on polarization of light in the Montana High School Polarization Photo Contest. My name is Andrew Hahn and I'm a second-year graduate student at Montana State University.
And my name is Martin Tauk, and I'm also a graduate student at Montana State University.
Okay. So what is this video about? Well, this video is about introducing you to the property of light called polarization. This property is utilized in things like polarized sunglasses. So on the left, you see a picture of a stream or a river without polarized sunglasses, with just sunglasses that are unpolarized. And on the right, you see that same river with polarized sunglasses, and you can see straight through. So we're going to talk to you, by the end of this presentation, you'll be able to actually talk about why that happens. Another thing, we want to show you some examples of polarization in nature, some things in like the sky or reflection off water, things you might not be aware of before. And we want to show you how to use polarization to take really good photos for our photo contest we're going to be putting on.
To start talking about polarization, we're going to start off with an experiment. And to kind of set the stage for this, we need to talk about 3D glasses. And you may have seen in movies from the 80s or movies about the 80s, people wearing glasses like this. And these are the type of glasses they use to watch 3D movies to get a 3D effect. And the reason they wore these is because when a 3D movie is projected onto a screen, you need two images, and you need a way to filter each image to each eye. And so they would project one image in blue, and that image would go to your right eye, and then they'd project the image in red just over it, and that would go to your left eye. But these days, 3D glasses look pretty normal. They look like this. The filters, each eye has no color dependence on it. And so the question is, how do these filter? And that's where our experiment begins. And since we're not able to perform that for you right now, what we'd like you to do is next time you're wearing 3D glasses at the movies or wherever, put them on and have a friend put them on as well. And as you're looking at each other, you should close one eye. And when you close one eye, you should see something. And what you see is something like this. And when you close the other eye goes dark. And so what we really want to do is have you understand what's happening here by the end of this presentation. And so we'll return to this a little bit later.
So before we can talk to you about what polarization is, we need to talk a little bit about what light is. And light is a propagating electromagnetic wave. So as it moves on the screen from left to right, you can see there's this little vector going up, and then it goes down for a bit, and then it goes up. Similar to the surface of the water, as if you can imagine a water wave moving from left to right. If you put a little bob on the water, it would move up and down as the wave moves. So this is a transverse wave. So again, just to reiterate, as the electromagnetic wave moves from left to right, the electric field vector, which is what that is, moves up in this case, and then moves down, and then moves up, and then down and up and down. So we call that polarization is what we refer to as the orientation of the electric field. So in this case, since the electric field is moving up and then down, pointing upward and pointing down, we call that vertical polarization.
So if we take this vertically polarized wave that we just looked at and kind of orient it a little differently here, and now let's say we look into that wave from the front. What we see is that electric field going up and down, and so we've shown that here in this XY plot, and like Andrew said, we call that vertically polarized light. But let's take another wave. This one we've colored red because we want to show that this is in the X plane. And so if you look into this wave, you would see that electric field oscillating from left to right. And so if we plot that on an XY plot, we see the electric field is only in the X direction, and so we call that horizontally polarized light. And now that we've seen vertical, we've seen horizontal, we can imagine that there are probably other orientations as well. And so if we take some amount of vertical light and some amount of horizontal light, equal amounts actually in this case, and we superimpose them on each other, the resultant we get from simple vector addition, tip to tail type of stuff, is this 45-degree oriented polarization. And so this 45-degree oriented polarization has both X and Y components as part of it. And we can see other angles if we take, let's say we take some y and less x this time, and we draw the resultant, simple vector addition, and we see that this is polarization at 20 degrees. So we can create any angle we want by modifying how much x or y components we have. So here we've put together an animation with the resultant vector as well as the x and y components in there. The blue again is the vertical, the red is the horizontal, and when you put those two together you get your resultant in yellow. And what we really want to drive home here is that they're all at maximum together, zeros together, and minimums together. And so they're always at these points together, and that's a property of linear light, of linear polarization rather.
So we've talked a lot about what polarization is, but how can we even tell if light is polarized? Your cameras, for the most part, can't tell the difference between vertically and horizontally polarized light, and neither can your eyes. So this is going to sound kind of circular logic here, but polarized light basically is what can be blocked with a polarizing filter. You have polarized wave coming in, and then you have this polarizing filter that you put. So we talked about how, for example, if polarization is vertical, if we put a horizontal polarizing filter in, it'll block all of the light. And so if we take two pictures and look at the difference, that's how we can start to tell if light is polarized.
So now that we know about polarization, we want to talk about how something even becomes polarized. And the first thing on our list is that light can simply start polarized. In some cases, certain lasers, just the way that they're manufactured, the way they're built, all the components inside cause the light to come out polarized. Computer screens are a source of linear polarized light usually. So this is one way light can be polarized. Another way is we can make it polarized by putting in a filter. So light can become polarized if we have, in this picture here, we have unpolarized light. Then we take a polarizer or a polarizing filter, and then the light coming through that is polarized. One of the most common ways to get polarized light is from reflections off of smooth surfaces at high angles. And this is kind of the effect you get when you have water and you get that glare off water. That glare is usually polarized, which is where the sunglasses can filter it out. And in this picture, we have the picture of a car windshield with no filter on top, and then on the bottom there we've introduced a filter. And you remember Andrew said pretty much the only way to tell if we have polarized light is to block it with a filter and see if anything changed. And so that's what we're doing here. In the no filter case, we see this tree reflection on that windshield. Windshield's a smooth surface, and that the light from the tree is hitting it at a steep angle, and so that's really bright in that photo. But in the filter picture, the one right below it, that tree is almost gone, and we can see inside the car. We see the person, the steering wheel, the headrest. All that light is coming through the windshield, and so we see that, whereas the tree light was reflecting off the windshield, and that caused it to become polarized and therefore blocked. Finally, you can get polarization through scattering in the atmosphere. And that just means sunlight, as it comes down into our atmosphere, it reflects off of little particles or bounces off of it somehow. And in that scenario, it often polarizes light. And a cool thing you can do to see this effect is you go outside on a nice sunny day, basically cloudless, and you determine where the sun is located, and then if you go 90 degrees from the sun, you're going to see a band of really dark sky if you're wearing polarized sunglasses. So it's important to have the sunglasses on and oriented correctly, but if you look up, you'll be able to see the polarization in the sky. And that's what we have pictured here is no filter. That sky is really washed out, but in the filtered image right below it, we've got this dark spot over towards the upper left, and it kind of gets brighter and brighter as we move away from that 90-degree mark from the sun. And this is the cool thing about this for photography, is that you can really see those mountains. There's much more contrast when you throw that filter in, because the skylight is polarized, but the sunlight bouncing off the mountains is not.
Okay, so what we're going to start with is a couple linear polarizers. So now that we've talked about linear polarization, we're going to see a few experiments and demonstrations. So to start, we're just going to take two linear polarizers that are just like this, and this one's loose and free to rotate, and the one down here is attached to this mount. And as I rotate this around, we see that the amount of intensity in that that's coming through doesn't change. And that's because our source here, this monitor that we've deconstructed, is a source of unpolarized light. And so when we take that unpolarized light and send it through one linear polarizer, no matter how we rotate that polarizer, the intensity of light coming through doesn't change as a function of angle. However, if we take two polarizers, so here's another polarizer just like the one on there, and if we take this and we put it into our setup here, like this, we've oriented these polarizers so that they're both vertical. And as I rotate this one, the top polarizer, 90 degrees, we start to see that light diminish drastically. And as I rotate it back out, we get light through again. So what I've done is I've oriented them both vertical, and as I rotate the top one, I'm rotating it into a horizontal state. And since horizontal is perpendicular to vertical, we've now crossed our polarizers and no light can come through because those electric fields are oscillating in such ways that one goes through the first one but not through the second one. And so we can do a lot of cool things with one polarizer, but we can do a lot of different things with two polarizers, like we've shown here. And we can put things in between here. That's why it's set up this way with a space. So for example, we have this third polarizer, and just like all the other ones, as I rotate it, it doesn't change. But I can take it and I can put it in between these cross polarizers. And as I rotate it around, you can see that the arrows on there indicating the direction of polarization. So as I rotate it, here we're oriented in line with the polarizer. And here we're oriented 45 degrees to that polarizer. And you can see that when I orient it like that, we get a lot of light coming back through. As I rotate it, we get more, and then less again. And then here we're at 45, here we're at 0 or 90, at 45, and so on and so forth. And so what's going on here, if you think back to some of the images we were showing you earlier, we have x and y components for any vector of light. We can break that down into x components and y components. And so when that light comes through the vertical polarizer, let's say where it's all in y, so we have all y light, but then we send it through a polarizer that's oriented at 45 degrees. Now we have half the light in y and the other half in x. So we've gone from everything in y to half y, half x. And what we do is when we go through the third polarizer, or the crossed polarizer up here, there's x and y components, so now some of that x light is coming out. So we came in with y, turned it into x and y, and then we let the x light out. And that's what's going on in this setup here.
So we're going to talk now about a polarimeter. And what a polarimeter does is it helps you determine if light's polarized or not. So normal photos, like this example, this grayscale, black and white picture is just taken with a regular camera, and the brightness in the image corresponds to intensity. Now a polarimeter, on the other hand, the brightness corresponds to the degree that the light is polarized, how much the light is polarized. So things dark in it is not, light that's not very polarized, or very randomly polarized, and bright things are things that are very polarized. So you can see some examples here. The first example you see, this car on the left, it's very dark. In the upper image, you see that the car is very dark. You can actually barely see it. And on the polarimeter image below, you can see this very bright. So that light, like we talked about before, light reflecting off smooth surfaces at a steep angle can create polarized light. And that's exactly what's going on there. Conversely, on the mountains here, you can see that the snow on the mountains, snow is very sort of a coarse material. It's not smooth at all. So when light reflects off it, it reflects randomly, and so that depolarizes the light. So it might be very bright in the regular image, but on the polarimeter image, it's very dark. You can't even really see the mountains. And this is a good example of one of the many uses of polarimetry. Is on the top right, you can't really even see what that blue arrow is pointing at. But on the bottom, you can see there's something bright there. So that means there's something smooth, something very probably shiny in that, and so that the military uses this, for example, to look for man-made objects. Because man-made objects are often smooth and metallic. So this is a good example how the polarization of light can show things that are otherwise hidden.
And here we have another image with intensity and then an image on the right that's been taken with a polarimeter. And we kind of see, we're looking for similar things here. Let's look, starting at the intensity side, we see the monitors are very bright, the wall is very bright, whereas in the degree of linear polarization on the right, the wall is very dark, but the monitors are still really bright. So let's take a look at what's going on here. The monitor is a good place to start. They're a source of light. They put out light, so they're bright in the intensity image, but they're also a source of linear polarization. So in the degree of linear polarization photo, they're very bright as well, meaning the light coming off of them is very polarized. And then the tabletops in the intensity picture are dark because they're made out of a dark material, but they're smooth and reflective, and light coming off of them at steep angles, we learned, gets polarized, and that's why the tables are bright over on the right image. The wall in the back is somewhat rough, and the light bouncing off of it is at a very shallow angle, so where you don't get a lot of polarization effects off of that, and that's why we see the wall is dark. And you might see some other effects along the corners and edges of tables and chairs, and these kind of surfaces can produce that polarization because there's light at certain angles, it's hitting it very steeply, and so those smooth surfaces produce that polarization effect.
So now we're going to talk a little bit about phase in the light wave. So waves have certain properties, amplitude, and frequency, but one that's going to become very important here in a minute is phase. And so you can just think of phase as the location of one of the peaks. But what we really want to know, what is really important, is something called phase difference. So if you have two different waves, they're superimposed on top of each other, the fact that the waves don't line up, and these waves have the same frequency and they have the same amplitude in this case, and we can see that these peaks don't line up, and we call that a phase difference or phase shift. So if we're talking about the y components and the x components being the same but actually having a certain phase shift, this can lead to something called circular polarization. So here's an example of a phase shift. So before, there was zero phase shift between the x and y components, but here there is a 90-degree phase shift between the x and y components. So you see before they were always at a max together and zero together and a min together, but here you can see when red is at a peak, blue is at zero, and when blue is at a peak, red is at zero. And the same thing, and it kind of oscillates around, so that the sum of these vectors, the length of that resultant vector is always constant, but the effect is it kind of corkscrews around, as you can see here.
Let's reintroduce the idea of indices of refraction and therefore Snell's law. And Snell's law basically says that different materials cause light to travel at different speeds within them. And the reason that light travels at different speeds is because the materials have a different index of refraction. And this change in speed causes the light to bend. So when you look into a pool of water, the bottom seems closer than it actually is. A birefringent material has indices of refraction that are different in the y direction and x direction. So we see in this picture here, we have ny, which represents the index of refraction in the vertical direction, and we have nx, which represents the index of refraction in the x direction, the horizontal direction. And these two, in a birefringent material, are not the same. And this can lead to some pretty interesting effects. So here we have a block. Down in the bottom, we have a block of birefringent material, and we have a wave that's 45-degree linearly polarized. So we have equal horizontal and vertical components. And let's take a look. Well, all we've done here is taken that 3D image and made it 2D, and that's what we've pasted up in the upper right. and the blue is vertical, the red is horizontal, but we've just made them so they're easier to look at. And you can see before they enter the cube, they are in phase, meaning their peaks are always aligned and their zeros and troughs are always aligned. And when they go into the crystal, the vertical blue light, since it's polarized vertically, that portion interacts with the index of refraction in the y direction, and the red light, the horizontal light, that interacts with the index of refraction in the x direction. And since those are different in a birefringent material, the speeds at which those waves travel in that medium are also different. And so we see the blue travels a lot slower, which gives it more time to oscillate within the crystal, whereas the red moves a little quicker than the blue and doesn't oscillate as much. So by the time they leave the crystal, we see that at the moment when they leave, the blue is at a 0 and the red is at a minimum. And so now we say they're out of phase. And you can see that that trend continues. When red is at a 0, horizontal is at a 0, the blue is at a peak or a minimum. And this leads to what we call circular polarization, or maybe some other polarizations basically. But circular polarization is the extreme. And so what we've done here is shown you those animations together. So we've already looked at these, but what we really want you to take away from this is in the top one, the circles are always together. They're always at a minimum or a 0 or a maximum, whereas in the circular case, the result in the yellow vector is always is constant. It's always at a maximum, and it just rotates around. But the blue and red still they look almost identical to the previous case. They've just been phase shifted. And so when the blue is at a maximum, the red is at a 0. When the red is at a maximum, the blue is at a 0. And this is circular polarization.
So now that we've talked about linear polarization and we've introduced you to circular and different types of polarizations, we're going to do some experiments and some demonstrations with birefringent materials. So to start, we're going to go back to our setup. So here we have just a linear polarizer over a unpolarized source. So remember, the monitor is unpolarized, and this is just the linear polarizer here. And birefringent materials come in all kinds of shapes and sizes, and they might be a little more common than you might think. So here we just have an ordinary protractor. It's plastic. It's got a little blue tint to it. But if we stick it on our linear polarizer here, we see that nothing's happened. It looks just as you'd expect. But if I take this off, just for effect here, and take our polarizer that's crossed and put it on top, so we've got basically no light coming through. Let me make sure it's oriented well. And now I take the same protractor and I put it in there, and we see a whole different effect. We've got all sorts of light coming through, different colors, dependent on where on that protractor it's coming. So we've got some spatial dependence in there. And it looks pretty cool. It's a cool looking object. And we know it's got birefringence because it's letting light through. Okay? And I'll put that back in a moment. But I want to show a different example. And that's with just a plastic bag. So this is a plastic bag that we have. And we can see if it's got some birefringence to it. And so I put it in here. And all of a sudden, we just get white light coming through, and a lot of light. And then as I rotate it, the amount of light we get through varies. And this is really important because a birefringent material needs to be angled properly in order for that light to be able to rotate the way we want it to. So if you put a birefringent material in there and you don't rotate it correctly, you're not going to get much light, if any, through. And so this is clearly birefringent because as I rotate it, we get light coming through. And when I rotate at different angles, we don't. But a cool thing about these plastic bags is we can introduce some stress to them. So I'll just kind of start to try and tear this bag a little bit. I'm not going to tear it, but I'm just going to apply some stretching to it, stress. And I've done that to a few points. You can maybe see it there. And as I put that in there, now we've got some colors coming through. And that's kind of the same idea behind something like a protractor. Just from the way that these are constructed, there's some plastic going there, and as the plastic, there's some plastic form that's being made, and as it cools, it might cool non-uniformly. And that non-uniform cooling causes these spatial variations at the molecular level. And that kind of helps one color make it out, twist to the right orientation to make it out of that second polarizer as opposed to another color. And as I rotate this now, you'll see the location of those colors might change a bit. So as I rotate it here, no, we don't really see it here. So let's try it on the protractor. It's a lot clearer when I do it on here. So as I rotate this, you can see it looks like those colors are kind of moving, almost like a wave or ripple in the water. They just kind of flow from one location to another. And that's because now as I rotate this material, those birefringent properties are a little different spatially, just on the molecular level, very, very small differences, but we can see it because the wavelengths of light are very small, so any minor imperfections come out. But there are some other birefringent materials that we can look at, or maybe some materials that we might expect to be birefringent look like they might be birefringent but actually aren't. So here we have a broken CD case. So let's see what this looks like. So we get some colors coming out of there. And again, as I rotate it, we get different colors in different locations. And right here, there's a pretty noticeable spot. And it looks like a lot of colors are coming out of there. There's a lot of small, quick changes. And that's probably where this piece of plastic was injection molded from. So that's where they were sending the plastic into the form. And so that place kind of cools differently than everywhere else. And so that's why all those colors are coming in there from the stress birefringent process. We've also got another CD case. Let's see how this one turns up. Some colors, not quite as interesting as the others. This one looks like it might be birefringent, and when we put it in our material, we see light coming through, so we might suspect that there's some birefringence. But as I rotate this, it's not changing, which tells us that it's probably not birefringent. And maybe all it's doing is, as light comes through it, polarized light comes through it, as it tries to go through that material, it just gets depolarized. So then we get X and Y and maybe some circular polarization, all sorts of weird stuff happening. But it's not really just rotating it in a very uniform way. It's just kind of scattering it ununiformly. And so one of the guys in our lab, he was working with heating materials that wouldn't normally be birefringent. And so what he's done here is he's drawn out MSU in a marker, and then he's taken a heat gun to it and traced out those letters with a heat gun. And so what he wanted to see is, as it cooled, would that non-uniform cooling introduce some birefringence? And so let's see what happens. It's a little bit big for this, but we can definitely see some birefringence around the letters. And over here, kind of away from all the heating, there's not a lot of color, but right around the outline of these letters, we get a lot of colors coming through. So we can start to see that, yeah, maybe this is birefringent induced from stress, from heating. This one, he did the same thing. You can't really see any imperfections in this, but if I put it under here, there's definitely a stripe right down the middle that he took a heat gun and caused these non-uniform heating effects to take place. And as I rotate this, we get light in and out. This one's really cool because it basically goes dark, and then we get all these colors back, and then it goes dark again, and we get these different colors moving around a little bit. But mostly we just get light out or no light out. And let's see, we have this piece, which is a piece of plastic, but you can manufacture the birefringence to be at a very exact to cause a very exact orientation change in your polarization. So these pieces of birefringent material have been engineered to create circular polarized light. So if I put it in here and rotate it, we get light out, and then we don't when I have it rotated at the wrong angle. And so this is specifically made to do this kind of stuff. And that's really popular. It's a really important thing for all sorts of applications. Camera filters, for example, use them. Circular polarizers, that is. And that's why you need these kinds of engineered materials. Not, this protractor has some birefringence to it, but it's kind of accidental. It's not intended. But we can intentionally engineer birefringence so that it has some use for applications we may have.
So now that you've seen this demonstration, let's actually just talk a little bit more about what you need to see this birefringence. So we saw that in the demonstration, Martin had always two polarizers with a little space in the middle. So because seeing birefringence requires some sort of polarized input. You have some, in this example, we have unpolarized light going through a polarizer, so now it's polarized, hitting a birefringent sample, which rotates some of the polarization and comes out the other polarizer. Now, this doesn't necessarily, your setup doesn't always have to look like this, but this just means that your birefringent sample has to be illuminated with some sort of polarized light.
And here we see some images from similar to what we had in the demonstration. It's the same protractor here, pointing out that the stress points, so the corners, produce a lot of light, a little more light than other areas, and that's because we saw stressing a material can cause it to have birefringent properties, and therefore we get these colors coming out of it. And here we have just a standard piece of tape reel, or a tape dispenser rather, and there's a lot of cool things happening here, but this one shows the stress a little bit better. You see this point over towards the right where there's just a lot of color variation over short distances, which leads us to believe that that's kind of the point of the plastic injection molding was happening there, or that was the entrance point. And due to the strange cooling effects or the non-uniform cooling effects, we get these birefringent properties.
So here's an example where we have this case, this plastic case on the table, and on the left you see there's no filter on the camera and you can't really see anything, and on the right you have a polarizing filter and you see this great rainbow effect that by now you're familiar with. It must mean there's some sort of birefringent thing happening there. So, but earlier we talked, we always had two polarizers for this, but here we only have one on the camera, so how can we see this effect with only one filter? And the answer is because I didn't say that there always had to be two polarizers. I said that there had to be, your birefringent sample had to be illuminated with polarized light, and in this case the polarized light is coming from the table. Unpolarized light is reflecting off the smooth surface of the table at a wide angle, which is creating polarized light, which then passes through the birefringent plastic, and then passes through the polarization filter on the camera, and that's what allows us to see the birefringent effect.
So now back to the beginning of this presentation when we did our experiment. Why does this happen? Why do we block out one of the lenses on our glasses when we close an eye? And you may be thinking, well, we've learned a lot about polarizers. Maybe these are linear polarizers, and you'd be on the right track. But a linear polarizer would, as you tilt your head one way or the other, it would change that intensity. As we saw in the demonstration, as that top plate was rotated, the intensity varied. And so this wouldn't really work in a movie theater, where if you tilted your head a little bit, all of a sudden the image is distorted or incorrect. And so the answer is, the way we're able to get the same effects as linear polarizers, but without the problems of rotation, is using circular polarization and circular polarizers. And so the way you build one of these is you take some birefringent material to rotate your vertical or linear or horizontal state into a circular state, and then block that out in each eye. And that's essentially what's going on here. The projections on the screen are, one image is right-hand circular and the other image is left-hand circular, and different images go to different eyes.
So now on to the photo contest. At the beginning we said we're going to teach you guys how to use polarization to make really cool photos. So hopefully you can do that now, but let's just talk about the photo contest guidelines. So we want you to take interesting photos showing or somehow using polarized light, write an explanation of the science behind the photos. The photos are going to be judged at Montana State by us, by the professors and some students. Judge 50% on the photo and 50% on the explanation. So if your photo is only so-so, but you have a great explanation, then your photo is still in the running. Contest opens April 1st and closes May 16th, and winners will be announced by the end of May. So here are some rules. The photos must be taken by students. Competition entries are accepted from April 1st to May 16th. Any camera can be used. Any filter or polarizing optic can be used. So if you have your fancy polarizer for your camera, for your DSLR, you can use both those things, or we will offer, when we come to your school, we'll offer these basic linear polarizers. Or, and now all photos must be accompanied rather by a single paragraph explaining the photo, how it was taken, why polarization is important, and what can be learned from the photo. All photos entered into the contest must be accompanied by a signed letter from your physics teacher at your school, and there's only one entry per student.
Prizes!
I'm keeping that.
So a photo contest wouldn't be complete without prizes, and we've put together a few for you. So the honorable mentions are going to be a trip to Montana State University. You come down to Bozeman, and we'll take you around some of the optics labs. We've got a few activities planned, including a holography event where you build a hologram and take it home with you. And so these are going to be, we'll have a few honorable mentions. And the grand prize is going to be a trip to the Kennedy Space Center, the NASA Kennedy Space Center in Florida. And that'll happen this July, this summer. And here's a few photos that one of our lab members took a few years ago when he won a trip down there. And we're really excited about this. There's a lot of cool stuff to be seen. You get to travel across the country and do stuff with space, which is always fun. So that's everything. Thanks for listening.
Thanks for watching.
Thanks for watching.